Welcome to this presentation. My name is Simon Helling and I am a PhD student at the Chair of Automatic Control at the ThA University. In this talk I will be going through the key concepts of the corresponding contribution to the ACC 2021, which is mostly concerned with obstacle modeling in model predictive control and under-actuated surface vessels using polyhedrons. First, let's look at an overview of what will be covered in this talk. This contribution is focused on path-following model predictive control, and in the background you can see a snapshot of a simulation for a path-following vessel in the Kiel Bay area. The goal of path-following model predictive control is to minimize the distance of the predicted vessel positions, which you can see in green, to the predicted reference path, which is denoted using black dots. When to beware on the path, or in other words, the time evolution of the reference path, is a degree of freedom to the model predictive controller. Therefore, a differential equation for the path parameter theta is introduced, which takes into account the desired service speed. Simultaneously to solving this path-following problem, the vessel needs to take a path that avoids obstacles. These can be either static or dynamic, and their dimensions along with the controlled vessel's dimensions are modeled using convex polyhedrons, as well as some safety distance, which you can see in red. Since model predictive control, as the name suggests, relies on a model of the system, I will go through the underlying vessel autopilot model first. The vessel is modeled as a 3 degrees of freedom surface vessel. The dynamic equations can be separated into a kinematic and a kinetic part. The kinetic part of the model is obtained by means of Kirchhoff's equations of motion and expresses the rates of change of the vessel's velocities u, v and r, which are shown on the left. In this equation the inertia matrix M arises and the nonlinear function tau includes all acting forces on the vessel, which, among others, are due to nonlinear drag and the rudder angle delta, which is the control input. This nonlinear function is approximated by means of a Taylor series expansion and assumes a constant forward speed u0. The kinematic part of the model connects the vessel velocities to the reference northeast down frame by means of a rotation matrix R. In this frame the position is given by x and y and the heading angle by psi, as can be seen on the left. Since we will be considering the explicit geometry of the controlled vessel as well as obstacles, here is how they are represented mathematically. The geometries are assumed to be convex polyhedrons. For this, a base shape can be defined, which you can see on the left, centered around the origin. Each face of this base shape is expressed using a half space, defined by a normal vector c tilde and some constant d tilde. Combining the normal vectors in the matrix capital C tilde and the constants in the vector d tilde, the convex polyhedron is compactly expressed with a matrix inequality. Using the position and the heading of the vessel, or obstacle, we can express the space currently used by the vessel or obstacle by means of an affine transformation. The next step is to include collision avoidance constraints between the controlled vessel and all obstacles in the model predictive control. For this purpose, the signed distance can be taken into account, which is a widely used concept in collision detection in various fields such as robotics, game physics and others. The signed distance of two objects is positive if they don't overlap and negative if they do. If the signed distance is to be included directly to the model predictive control problem, approximations need to be used. Therefore, a dual reformulation of the signed distance is implemented, which is exact, smooth and differentiable. In order to derive this dual reformulation, we need to introduce some basics of convex geometry. Every convex shape is completely described by a support mapping given by the equation on the top right, which gives the maximum inner product for a direction z and therefore defines the support point, which you can see on the left as the black dot. This point is always element of the considered convex shape. The direction z together with the support point s can be used to define a supporting hyperplane and half space, which you can see as the dotted line and the diagonal space left of it respectively. The convex shape is then given as the union of all supporting half spaces. So you consider every possible direction z, which then gives a possibly different support point and therefore also a different half space. In the contributed paper you will find the derivation of the full body case, meaning that both the controlled vessel and the obstacles are considered as polyhedrons. Here we focus on the point case, which can be extended to the full body case. Thus, the controlled vessel is assumed to be a point, while all obstacles are of polyhedral shape. The fundamental observation is that the signed distance between any arbitrary point x bar and a supporting hyperplane for a given direction z can be evaluated using z x bar and the support point s. For example, in the upper figure on the left-hand side, you can see that x bar lies in the half space defined by z and the support point s. Thus, the signed distance between x bar and the hyperplane h is negative. In the figure below, another direction z is considered. For this particular choice, the signed distance is positive, since x bar does not lie in the half space defined by this other direction z prime and its corresponding support point. This observation yields the signed distance between the point x bar and the obstacle O as the maximum value of the signed distance between x bar and any supporting hyperplane given by the direction z. Thus, one would need to find the direction z where the above-mentioned inner product yields the largest value. For collision avoidance, though, it suffices to find any direction z, such that the signed distance is larger than a user-defined safety distance ThA15. Now at this point we derived an expression for the signed distance as a maximization problem. This optimization problem can be reformulated by means of the Lagrange dual problem, which is more often than not easier to solve. Therefore, the definition of the support point is inserted and replaced with its dual formulation, where a dual variable mu is introduced. Finally, this dual variable is included as part of the path-following model predictive control problem, along with the inequality constraint in the gray box, which expresses the dual reformulation. If there is a mu such that the inequality holds, the signed distance is larger than the safety distance, and therefore collision avoidance between the controlled vessel, given as a point, and the obstacle is ensured. Now that we derived the dual collision avoidance constraints, we can take a closer look at the path-following MPC problem again. Using the dual approach, we have additional dual decision variables next to the control input u. The cost functional j realizes the minimization of the predicted positions to the reference path. The minimization is subject to the vessel system dynamics, as well as the differential equation which dictates the path propagation, also known as the timing law. The collision avoidance constraints are compactly written as the ZCal, which is denoted with a calligraphic X. Note that slack variables epsilon are also included as decision variables, which achieve soft collision avoidance constraints. On the left you see the desired path-following behavior realized by the timing law. If the vessel is far away from the path, the predicted path points are closer together, which signifies that the path parameter changes slowly, which you can see in the blue circle. If the vessel is close to the path, however, the path parameter can change faster, which results in the points being further apart from each other. This behavior is shown in the red circle. Here the details on the timing law are shown, which achieves the desired path parameter dynamics. Based on the path parameter theta, the predicted path points are calculated given a set of predefined waypoints, and the predicted path points lie on the line segment connecting these waypoints. Typically, obstacles are modeled as circles, or more generally as ellipses. Therefore, it makes sense to compare the dual polyhedral approach to this use case. In the following video, you will see the same scenario for an ellipsoidal and a polyhedral implementation. As can be seen, the ellipsoidal formulation cannot take into account the controlled vessel's shape and is possibly less well suited for confined environments because it overestimates the vessel's dimensions as well as obstacles' dimensions. The dual reformulation can take into account the explicit geometry, but this approach comes at the cost of additional decision variables in the MPC problem. This leaves me with the concluding slide. Thank you for your attention and I wish you all the best.